This is an example of a problem in the AC Mesh Solutions game in Circuit Tutor at level 4, or the mastery level. As always, we have multiple levels of examples available, and it would be a good idea to view some of those prior to starting the actual problems. So let's go into a mastery level exercise. Okay, and we notice that the mesh currents have already been defined for us here. That would actually be the first step in the problem. And of course we had to select a reference mesh, which by default in Circuit Tutor is being selected as the outer mesh, the one that would have a counterclockwise mesh current here. So that mesh current has been set to 0 in this problem as the reference mesh. Okay, so because it is a solutions problem, we are being given the KVL equation. In this case, there's just one for a single super mesh going around the outside of the circuit. And we don't need to write that, but we do need to come up with the current constraint equation for the one current source, as well as the equation for the control variable of the dependent voltage source, this voltage controlled voltage source here. And we also need a SOT variable equation for the voltage V0, which in this case is the voltage of the independent current source. So let's go ahead and do that. We'll do the current constraint equation first. And we observe that we actually have two mesh currents that are going through this current source. So therefore we're going to need a difference of mesh currents. And that will be equal to the fixed value of that source. Because it's an independent source here, we just use this term. And that value we can fill in, the value of I1s is found down here. That's just 1 angle 0 degrees in this problem, amperes. And now we have to examine the polarity so that we notice that I1 is traveling clockwise in the lower mesh, which goes through the current source in the direction of the reference arrow there for that source. So that would be the one then that will have the positive sign in the equation. So we have I1, and then I2 is traveling clockwise in mesh 2, which goes opposite to the direction of the reference direction of the source. And therefore that must have a minus sign for I2. So we'll check that, and that is correct. Next, let's do the control variable equation for the voltage controlled voltage source here with a dimensionless gain of 2. So we'll select control variable equation, and it's the control variable here is Vx. Remember, the output value of the source is 2Vx, or in other words, Vx is doubled on the output. So we'll select writing an equation here for Vx, and we'll fill in the x there. Remember, the alpha indicates that you're supposed to fill that in with an alphabetical character. And now we look and see Vx is the voltage in this case of a resistor. And there's a single mesh current here, since the outer mesh current has been defined as 0. There's a single mesh current going through that resistor. So we will need basically that multiplying the resistance. So we need an Ohm's law type of equation. Of course, these terms would not be dimensionally consistent with a voltage, and so those are automatically going to be wrong. Okay, so the current going through that resistor is I1. So we'll fill that in, and the value of the resistor, of course, is 4 ohms. But now we need to be very careful, as always, when using Ohm's law, or any similar law like V equals IZ for an impedance, to make sure that we have the proper sign. Remember, half the time, roughly, it's going to be a minus sign, so we need to check that carefully. So we observe that I1 is going clockwise and going into the negative side of the defined control voltage Vx. Therefore, that would be the active sign convention, going into the negative side or out of the positive side. Because of that, Ohm's law then has a negative sign, and we need to have a negative sign there or we will have an error. So we'll go ahead now and check that, and that is correct. And then finally we need to write a SOT variable equation for the branch voltage across the current source. So we select SOT branch voltage to get the proper palette of terms here, and that will be V0 equal 2. And now we have to remember, this may be the tricky part of the problem, is that the voltage of a current source is whatever it needs to be, right? It does not have any value defined by the source itself. Instead, this source has a fixed current of 1 amp. It does not have, however, a defined voltage. So how do we find that voltage then? Well, any question in mesh analysis, the answer is nearly always going to be KVL, because after all, mesh analysis is based on a systematic application of Kirchhoff's voltage law. That's why we have KVL equations and not, for example, KCL equations that we have in nodal analysis. So the answer is nearly always KVL. In fact, that is the answer here. So we need to use Kirchhoff's voltage law to determine this unknown voltage. That's the only way that that can be done. Now, that means we have to construct a closed loop in the circuit. And we have really two choices here. We could do one with mesh 1, or we could do it with mesh 2. Typically, we're going to pick the one where the equation will be simplest and have the fewest terms. And we see that there are 3 elements in mesh 2 and only 2 elements in mesh 1. So mesh 1 would probably be a better choice. Now, Circuit Tutor will accept either valid equation here, as long as you do it correctly. But we're going to do the one for mesh 1. So we want to have voltages. I mean, if you like, you could actually add it up, saying you add the voltage drops around that mesh, for example. Now remember that the defined polarity Vx has absolutely nothing to do with this. That simply controls how this voltage controls a voltage source. That has nothing to do with the voltage drops in this circuit, and so that should be ignored, as should the polarity of, well, the polarity of V naught is relevant only when you're doing that voltage drop. But so for example, you could add the first voltage drop would be I1 times 4 ohms. The next voltage drop, since you're going from plus to minus, would be simply V naught, and the third voltage drop would be I1 times J9 ohms. Notice the passive elements here, if we go clockwise in the direction of the defined mesh current, we have positive coefficients, because we're using passive sign convention in that case for the voltage drops. So we could add that together and then solve for V naught. Alternatively, I can just kind of reason about what V naught would be, and notice that these terms basically would have like a plus and a minus here if I use passive sign convention, which is opposite to the defined direction of V naught, because it would be put plus connected to negative and negative connected to plus. So both of these passive elements, for the same reason, are going to have minus signs. So I will need one mesh current, again, because the outer mesh current is 0, multiplying each of 2 impedances. Now remember, as always, when we write this type of KVL equation, or for that matter, a KCL equation in nodal analysis, regardless of what type of equation it is, we always need to have a separate term for each circuit element. So we can't combine those mentally into 4 plus J9, for example. Even though that would be mathematically valid, it will not be accepted here. So we're going to put in the mesh current I1 in both places, and then this will be the one for 4 ohms. This will be the one for J9 for that impedance. And then, as we said, each of these must have a minus sign, because in both cases, and again, it's not the Vx signs that are relevant here. That's not relevant at all. If the Vx signs were reversed, this would still be minus in both cases. But what does matter is that the mesh current I1 is flowing into the positive side or a drop. So, and because that positive side here basically corresponds to the negative side there, that's why we have the minus signs in both of these terms. So we need to change that to a minus and this to a minus. And then if we check that, that will be correct. And that's the same conclusion you would get, as I said, if you added the voltage drops going in a closed surface there, a closed loop, I meant, not a surface, closed loop. Use surfaces in nodal analysis. Okay, so that is, since we had only the one slot variable, we are done writing equations now for this. And we can always check to make sure we have the right number of equations. We have 1, 2 unknowns here, but actually 3, because there's also a control variable. So it's actually I1, I2, and Vx. So we need 3 equations, therefore, to solve for those 3 unknowns. And here we have 1, 2, 3, neglecting the slot variable equation, which I'm treating separately. So that would be sufficient. So now I can click No More Equations. Now, because this is a solution problem, we need to solve these equations. We're not going to use this one just yet, but just these first 3. But prior to doing that, we're basically going to put them into standardized form, which just makes it a little easier to solve by combining, for example, the coefficients of the different I2 and I1 terms here. Again, we can multiply by a constant if we wanted to do that, or divide by a constant, but for each equation. But we cannot for example, substitute this into here or this into here or anything of that nature at this stage. We'll do that only when solving. So here's our form, and again we have 3 rows here for each of the 3 equations. So the first one, the constraint equation, just says I1 minus I2 is 1 angle 0. So that means the coefficient of I1 will be 1, as it is in this equation. Coefficient of I2 will be negative 1, and then the right-hand side will be 1 angle 0. Okay, the next equation is the KVL equation, which is a little bit more complicated. So here, for the I1 terms, we see we have a coefficient of 4, dropping the units here. And then down here we also have J9. So combining those two, just adding them, that will give us 4 plus J9. We'll just add those 2 complex numbers in our head, which is easy to do. I2 now has a coefficient of, well, there's one of 3, and then there's negative J8. So that will be, again, combining those 3 minus J8. Then Vx in this equation has a coefficient of negative 2, because that does appear there. So we have a negative 2 times Vx. And then, if you notice, there are actually no constant terms in here because there are no current sources in this. Because remember, this was actually written for a super mesh going around the outside, and there's no current source on the outside loop. So that right-hand side will be 0. And finally then, we need another equation for the control variable. So here, let's bring everything over to the left side. I mean, it doesn't matter, either way would be accepted, but I'll just bring it over to the left side. So that means Vx will have a coefficient of 1. And then I1 will have a coefficient of 4 when we put it over on the left, adding this I1 4 to both sides. So that will be plus 4, because we have put it on the left side of the equation. And then the right-hand side of the equation, of course, will be 0, since we put everything on the left-hand side. So now we should have our complete equations here. So we'll check that. And those are correct. Okay, so now those have been printed on the screen for us here. Sometimes you might need to scroll if you're using a smaller monitor, but they'll be there. And now the goal is to solve these. But before we do, just for reference, we're going to cast them as a matrix equation, even though we probably almost certainly will not want to use matrix methods to solve this problem, because that would just be overkill on such a simple problem. But in any case, that's very easy to do here. We just click the Copy from Simplified Equations button. That just takes these same coefficients and puts them into the matrix and the constant vector here. And remember that each row of the matrix equation corresponds to one of the original simplified equations. So for example, we have 1 I1 minus 1 I2 plus 0 Bx equals 1 angle 0. That's the first equation. And similarly for each of these other rows. Okay, so we'll check that. And that is correct. And now, of course, the job is to actually solve these equations to find the mesh currents. Now, ultimately, of course, we want the SOT variable, which is V0, and you notice that only needs really I1, not so much I2, because I2 doesn't appear there. Nonetheless, we may want to solve for both those variables, but we really need I1, so we can keep that in mind here. Okay, and we're going to use elementary algebra. You could, in theory, take this matrix and put it into MATLAB or an online calculator, something of that nature. But on a test, for example, typically you would not have access to those types of tools. So I'm going to show you how to do this by hand, which I think is by far the easiest way to do this. And your instructor may want you to retain your algebraic solution or even turn that in. So if so, turn that into them if they request it. And if not, you probably want to have a record of that just for your own records and your own studying purposes when you come back to review how to do this type of problem. Okay, so there's the form to enter those values. Again, we could skip this and go straight to entering the SOT variable if we like, but I'm just going to enter the mesh currents first for completeness. Okay, so we're going to do the algebra here on paper. And so what I've done is I've just typically what you want to do is to take these simpler equations, which are the current constraint equations, and the control variable equations, which are never very complicated, and substitute those into the more complicated equation, which in case we have only one KVL equation. And by doing that, we can eliminate all but one of the unknowns, and one equation and one known, well, that's never terribly difficult to solve. Now, remember that we are in doing algebra with complex numbers. You do it exactly the same as you would do with real numbers. It's just that you have to do complex arithmetic now instead of real arithmetic. But otherwise, the principles are exactly the same as what you learned in high school algebra. So here I've copied over the KVL equation in the simplified form, rather, which is the second row here. So we have 4 plus J9 I1 bar plus 3 minus J8 I2 bar minus 2Vx bar equals 0. And then I've also written the constraint equation and the control variable equation for reference. So I1 minus I2 is 1 angle 0, or just 1 for short in rectangular form. And the Vx bar is just minus 4 I1 bar. And our goal here is to substitute it in. Remember that we do need I1 ultimately, so we may as well get rid of I2 as opposed to getting rid of I1 in this equation. So I've solved this first equation for I2, just adding I2 to both sides and subtracting the 1, of course. So we have I2 bar equals I1 bar minus 1, a nice simple equation. And then the Vx is already solved, so we can substitute that. So now we rewrite this equation here, down here. We retain the I1 bar term, but then for the I2 bar, we have the coefficient, but then we replace that with I1 bar minus 1 for this relationship from the current constraint equation. And then the minus 2 Vx bar, well, remembering that Vx bar is minus 4 I1 bar, plugging this in here, that will just give us plus 8 I1 bar. Remember, the minus signs will, of course, cancel out there where they multiply. And now we just have the equation in the single unknown, I1 bar. So let's collect those coefficients to simplify that, which we can do by hand. So we have here, for real coefficients, we have 4 plus 3 plus 8. So that would be 7 plus 8, or 15. And then the imaginary coefficients would include J9 and negative J8. So J9 minus J8 is just J, and that would be it. So we just have plus J, or J1 if you prefer, times I1 bar. And then the constant term here would come from this minus 1. And so that would basically be the 3 minus J8 times minus 1. We can add that to both sides to put it on the right-hand side where it belongs, and that would, of course, just give us 3 minus J8 on the right-hand side because it has this coefficient of negative 1 here. So we just add that to both sides. And so we just have this simple expression here, and so we need to compute 3 minus J8 divided by 15 plus J to get I1 bar. We can do that on a calculator, and while that's very simple, I will just illustrate it briefly using a TI-84 Plus emulator. And one thing to remember, as always, we must be in a suitable complex number mode. In this case, we want our answer to be in polar mode. If you see real up here, then you certainly will not get any right answer doing complex number calculations. Also, because Circuit Tutor requires degrees, I want to be in degree mode. So if that wasn't already correct, I would go into the mode here and use the arrow keys to go down here and then put this into the appropriate mode, which in this case would be polar. And then also make sure that you're in degree mode here. When using polar form, the radian degree does matter. Okay, so we'll go back out since that's already done and just enter that expression. Now remember, we do have to use parentheses around complex numbers, otherwise the order of operations is such that we would not be actually doing what's written here. So we need parentheses, and then we'll go 3 minus, and now we use I. So we go second I, that's where the I is on the decimal point key. I times 8, close parenthesis, divided by the 15 plus J. And remember, if you use those numerator over denominator templates, those, depending on exactly which model you have, those may or may not work. So I would typically recommend just doing it the old-fashioned way like this. Okay, so we then have to open parenthesis here for the denominator, 15 plus J, which in this case would be I, close parenthesis. And again, if you eliminate, if you omit any of these parentheses, you will get the wrong answer because you're not doing what is expressed here. So that's very important to make sure you use parentheses correctly. Okay, so we just enter, and we have 0.5683 to 4 significant digits, angle negative 73.26 degrees here, again, carrying out 4 digits. And again, it's important to remember that you are in the degree mode. If you're in the radian mode, then obviously this would not be in degrees. And that's one of the common sources of error that people have, is not paying attention to the degree and radian mode. Okay, so that's very simple. And then for I2 bar, we just need to take that value and subtract 1. So I can just subtract 1 from that answer, and that would give me 0.9978, angle minus 146.9. Now, Do be careful that you could not enter this number if you wanted to retype it for some reason. You could not retype it as written because, again, the calculator, even though it will print out results in degrees, will not accept them in complex exponentials in degrees, which is a rather odd feature of this calculator, and that applies to both 83 and 84 models. The TI-89 does not have that issue and would accept it in degrees, but the 83, 84 unfortunately do not. So that's our result there, and then anticipating that we're going to need the v-naught prime, I'll just show that right now. Remember this SOT variable equation, we had basically negative I1 times the quantity 4 plus J9 if you factor out the minus sign. So I've just written that here. v-naught bar is equal to 4 plus J9 times now the I1 bar, which is this value here, which I've copied down, and then just evaluating that on the calculator. Since I've got the calculator out here, that would be, let's see, well, I want actually this value. So, I mean this value rather. So I'll just re-enter that. Let's see. Although I could actually go up just for simplicity here and select this. Now remember, I cannot select the answer, unfortunately, because that's in the wrong form. That would not be, if I select that to copy it down, it will not work correctly. But I can just do the expression because that'll still evaluate to the same number. And then multiply that by the negative parenthesis 4 plus J9. So 4 plus the I9. And it looks a little odd with that minus sign there, but that will work. And that should give you the correct answer. So that would be 5.597, angle 172.8 degrees, again, to 4 significant digits, just to preserve accuracy in the answers. And that would, of course, be in volts, since that's a voltage there. Okay, so now let's enter those mesh currents initially, since we're really back at that step here. 0.5683, and then again the angle is negative 73.26 degrees. Remember that currents and voltages are always entered in circuit tutor in polar form in AC problems. And so the I2 bar would be 0.9978, angle negative 73.26. And again, the units are supplied for us. If you're doing this on paper, got to make sure to write always the units with your answer because that's not really a correct answer without units. So we'll check that. Oops, I may have made a mistake there. So I2 bar, did I copy it wrong? 0.9978. Oh yes, I just read off the wrong line there. So I just mistyped that. My apologies. So that would be negative 146.9. So it would have been good probably to check that before I entered it. And notice both the magnitude and the degree angle are marked wrong because the computer can't distinguish whether, for example, well, it just always does both, basically. So check that. That's now correct. And then the final step would be to enter that SOT variable number, which we've already computed here. So that's going to be the 5.597, angle 172.8. And again, that's degrees and the volts is there. So we check that, and that is correct. And then the final step would be to put the SOT quantity in the time domain, that is to do an inverse phasor transform to compute V0 in the time domain. So in order to do that, notice that we, first of all, are always using a cosine function. Now that's given to you in Circuit Tutor, but if you're doing it by hand, you simply have to remember that the result in the time domain based on a phasor will always be a cosine function, not a sine function. So that's just something you have to learn. And then the argument of the t, and don't forget that t, because if that's not there, it's written for you here, but if you forgot that in paper, then this wouldn't obviously be a function of time, and it wouldn't make any sense to write that as v0 of t. It would just be a wrong answer. So that has to always be omega, because omega, by definition, is what multiplies t in the argument of a cosine or sine. So here we're actually not given omega, we're given f. We're given f as being 40 hertz rather. And hertz, remember, is a cycle per second, not a radian per second. So we need to multiply this times the number of radians in a cycle, which is 2 pi. So 2 pi times 40 would be 80 pi. And we can just evaluate that quickly on the calculator. So that would be 80 times pi, just to get it accurately here. And that's 251. That's probably enough accuracy. So just do 251. Okay, so we'll put 251 in there. And do remember that it doesn't accept metric prefixes in this argument. So if we had kilohertz, for example, or kiloradians, then we'd have to put 000 or what have you to put it in the proper form, which is just a number. Okay, then the V0 coefficient, here it's 5.597. Remember that the magnitude of the phasor is always equal to the amplitude of the cosine function, and then the phase angle of the phasor is the phase shift in the cosine function, the 172.8 degrees. And of course that's volts, which on paper you'd have to make sure to write volts there, because it could be millivolts or nanovolts or something like that. Okay, so that is correct. And that basically finishes that problem. If we did want a more detailed explanation, for example, of how that KVL equation was written, or just to confirm how the SOT variable equation is constructed, we can request the more detailed explanation here. And then it'll give us the details, show us the voltage drops around the loop, the way that the super mesh is constructed. There's very detailed explanation available here if you need that. And of course you can explain dependent sources or control variables in general, or constraint equations in general. That's all available here if you need to review any of that. So that does complete this problem.